Okay.
Today the speaker is Michele Ronchi, which is doing the PhD with Nanda Rea and Vanessa Graver in the magnesia group, and he will speak about galactic distribution of neutron stars with machine learning. Please, Michele, go ahead.
Okay, thank you very much, Daniele, and thank you to all of you to be here today. In my talk, I would like to present you our recent advances in our work in population synthesis of galactic neutron stars. And so I work mainly with Vanessa Graber and also Alberto Garcia. Here in this talk, I would like to concentrate on recent work we submitted, and it's about analyzing the galactic distribution of neutron stars by using machine learning techniques. So first of all, let me start by introducing neutron stars a little. So as you might know, neutron stars are really compact objects that are born in supernova explosion from rather massive neutron stars, and they are characterized by they are spinning very fast, and they are characterized by a very powerful magnetic field. And so the combination of these two effects ensures that they are really interesting objects to study, since they can emit almost every kind of radiation, from radio to X-rays to gamma rays. And traditionally, when talking about neutron stars, one show this kind of plot, which is the PP dot plot that show the period derivative on the y-axis versus the spin period of the stars. And as you can see, there are a lot of classes of neutron stars. The bulk of them are the so-called normal radio pulsars that are detected basically in radio and are believed to be powered by mainly the rotational energy. But there are also other classes. Among the most relevant, we can talk about the magnetars, which you can see on the top right, which have a very strong magnetic field, up to 10 to the 15 Gauss, and they are believed to be powered by mainly magnetic energy, and to emit very strong X-ray pulses and powerful transients. Or another class of neutron stars is the binaries, for example, which are believed to be, or you can see them in the bottom left of this diagram, and they are mainly old objects that have been recycled by accretion processes from a stellar companion. So they spin very, very fast, but they have a very low magnetic field due to the fact that they are old. So our main project is to try to develop a population synthesis code that will be able to explain all these different features of the neutron star population. And so it will try to take into account all the electromagnetic bands from radio to gamma rays. But today I would like to concentrate more on the dynamical features of the population of isolated neutron stars, especially of the radio pulsars, that have been the topic of our recent work. So what we know about the distribution of neutron stars, in particular isolated neutron stars in our galaxy. Here I show the sky map of the neutron stars we know to be isolated. We know almost 2,000 of them, and we also have an estimate of the distance thanks to the dispersion measure, which is available from radio observations and the free electron density model we use for the galaxy. And only 10% of them, so nearly 200 of them, has also measurement of the proper motion. And here I show you the magnitude of the proper motion of the stars projected in the sky through the length of the lines associated to each star. And so we know basically only the projection of the proper motion. We do not have access in general to the line of sight velocity. But what is relevant is that neutron stars have very high proper motion, which can reach up also 1,000 kilometers per second in some cases. And several studies have been performed in order to try to study what is the origin of such proper motion, such high proper motion. And one of the best explanation is to explain the origin of such proper motion with a kick which is imparted to the newborn neutron stars during the supernova explosion. And several authors have studied this, the distribution of the possible kick velocities at the birth of the neutron stars. And but there is no consensus at all on the shape of this distribution. For example, in 2005, Hobbs find that a Maxwell distribution best describes these birth velocities. But 1 year later, Faucher-Siguer and Caspi models this velocity with a double exponential. And more recently, two works have pointed out that maybe the best description for the birth velocity is a two Maxwellian model with a low tail, and so a bimodal Maxwellian with a low velocity part and a high velocity part. And this also can have a physical explanation related to the different origins of the neutron stars. For example, the high velocity part could be explained by neutron stars that are born from core collapse supernovae with from a massive star that has developed a pretty massive iron core. And on the other side, for the low velocity tail, the possible origin is from supernova explosion where the progenitor star has developed a small iron core, and simulation have shown that is associated to a lower kick velocity imparted to the newborn neutron star, or from electron capture supernovae, which are developed mainly in such stars that do not reach the iron core stage, but they developed a degenerate core of oxygen, and mainly of oxygen, magnesium. And if this core reaches a threshold mass, which is around 1.3, it could undergo a collapse due to electron capture, basically. So this is just an overview of what we know right now. And so what is our main objective? The main objective of our work. So we tried to reconstruct the dynamical properties of the population of neutron stars by looking at the population as it is right now. So right now we see, of course, an evolved population since neutron stars have been wandering in the galaxy and it's been subject to the galactic gravitational potential. And so our question is, can we reconstruct the birth properties by looking at this kind of population? And our approach is based on simulations. So we focus mainly on constraining two features, the birth kick velocity and the birth position in Galactic 8 of the population of neutron stars. And to do that, we simulated different population of neutron stars, starting from different initial conditions. And the second step is to train a neural network on these simulations in order to reconstruct the birth properties, in particular the birth kick velocity and the birth position in Galactic 8. So let me start by explain a little how it works, developing a population synthesis code. At least for the dynamical evolution part, there are several ingredients that should be developed. So we use a Monte Carlo approach. So we start from some model and we basically draw from this model the initial conditions. And so the first thing is to choose a birth rate history for the neutron stars. And to give an age to them. Then we have to assign a birth position, a birth initial velocity, and then by assuming a galactic gravitational potential, we can then evolve in time according to the age of each neutron star by simply solving the dynamical equation. So let me start from the first step. So we know that neutron stars are born from massive progenitors that are OB stars mainly, and they at the end of their life they explode in supernova and they form neutron star. Our recent work has found out from several observations and several data that the current estimation of the supernova rate in our galaxy is around 1.6 core collapse supernovae per century. So just to be simple, we assume birth rate of the neutron stars, which is 1 neutron star per century. And we choose a maximum age for such neutron stars that is 10 to the 7 year, mainly for computational reason, and also because stars that are older than 10 to the 7 years basically are very difficult to be detected since they emit very low electromagnetic radiation. So at the end, by assuming this birth rate, we simulate 10 to the 5 neutron stars in our simulations. Then the second step is the birth position. We assume a galactic. Yeah, sorry. Okay. So we assume a galactic shape, basically, and we start from a radial distribution of neutron stars that has been studied by Yusufov and Kusuki in 2004, which has a peak at around a few kiloparsec from the galactic center. And then we assume a spiral arm model, since spiral arms are believed to be region of active star formation, and so massive stars are mainly concentrated in these regions. And finally, we assume an exponential disk model to model the birth position in galactic 8. And here is the one of the two free parameters we are going to vary in our simulations in order to simulate different initial conditions, which is the HC parameter, which is the scale 8 of the exponential model here. Then the second part is to model the birth velocity, and this is done by taking into account the contribution of two velocities. The first one is the velocity of the progenitor in the galaxy, since we know that the galaxy has a rotation curve which depends from the mass inside it, and so and of course from the gravitational potential of the galaxy. And so the progenitor is subject to this gravitational potential, and we assume for simplicity that it moves on circular orbits due to this gravitational potential of the galaxy. And on top of this, we have to take into account of the kick velocity, which is imparted by the supernova when the neutron stars are born. And to do so, we assume the single parameter model, which is the Maxwellian distribution, again, just for simplicity. Here, the free parameter is the dispersion sigma k of the Maxwell distribution. So we have to sum these two contributions. Then, before evolving, we have to choose a galactic model, and we choose one of the most recent one, studied by Bovi et al. In 2015, and used also in some Gaia, in recent Gaia papers by Marchetti et al. In 2019, for example. And it is basically a 4-component model with a nucleus, a bulge, a disk, and a halo. So let's come to the dynamical evolution now. So after setting up the initial conditions, what we do is to make different populations of neutron stars by varying the sigma k parameter of the Maxwell distribution from which we draw the kick velocity. And by varying also the scale 8 HC of the exponential disk, we used to draw the birth distances from the galactic plane. Then we evolve in time according to the age of each neutron stars, the world population, and the final output, that is the final positions and the final velocities of the stars, are encoded in position and velocity maps in equatorial reference frame. So just an example here for a simulation with sigma k 265 kilometers per second and with a scale 8 of 0.18 kiloparsec. We have three maps that we use, which is a density map that encodes information on the final position of the stars, and two proper motion maps, one for each component of the proper motion in the RA and DEC coordinates, respectively. And so for each simulation, we have this set of maps that we can use. And each set of maps is labeled by the value of the two parameters, sigma k and hc, that has been used to simulate them. So here, for example, just an example of how the density maps looks like by keeping fixed the sigma k parameter and varying, for example, the scale 8. So you can see that, for example, there is a slight increase in the broadening of the stars in the density map when an HC of 0.5 kiloparsec is used. And also in the proper motion, you can see that the average proper motion get more blurred and more mixed up as the galactic 8 increase, due to the fact that stars are far away from the galactic plane. And here, for example, is the opposite effect. So by keeping fixed the HC parameter and by varying the sigma k, so the kick velocity, and again by augmenting the kick velocity, you see the increase in spread of the stars at the end of the evolution, and also more mixed up velocity, more mixed up proper motion in the proper motion maps. So this is the part on the population simulation. Now let's move to the second part, so artificial neural networks, and I will explain how we are going to use them. So first of all, artificial neural networks, they are called this way since naively we can think about an analogy with biological brains. So basically they receive an input, an excitation from the external environment, and on this they process an output. And they have been used mainly for two kinds of problems. The first one is a classification kind of problem. So for example, if you have a data set with different class inside and you want to distinguish between one class and another, you can train a neural network to do that. Or the other problem is a regression problem. So for example, you have a set of data and you just want to fit a model to this data, and also a neural network can learn to fit a set of data. So usually neural networks are formed by successive layers of neurons, which is the building block of the neural network. So what is a neuron? A neuron basically receives as input the signal coming from the previous layer of neurons, and it processes this input first of all by making a linear combination of these input signals through some weights that are indicated here by the W, and a bias B. And then this linear combination is passed through a nonlinear function in order to add some nonlinearity to the process. And the output of this is sent to the other to this subsequent neurons in the other layers. So here the weights and the biases are called the network parameters, and are the parameters that given an input determines the final output of the neural network. So for our kind of problem, which is a regression problem, since we are giving as input the density and proper motion maps, and we want to decipher them and to predict the value of sigma k parameter and HC parameter that being used to simulate them. So this is as a kind of regression problem. And we use a convolutional neural network that has been proved to be really powerful in decoding information contained in 2D maps, 2D representations. And so convolutional neural network is formed basically from convolutional kernels or filters that basically recognize the features inside the maps you are passing as input. So for example, in this here, I show you how a convolutional kernel can extract, for example, the information on the edges of an image. And then the second block of a convolutional neural network is what is called a max pooling layer, which is another filter that basically is able to extract the most relevant features in the image processed by the convolutional filter, and also to reduce the dimensionality of the information, so that the training proceeds faster and is more effective. And at the end, after an alternance of a convolutional filter and max pooling layer, usually there is a set of linear layers that are used to gather all the information coming from the previous layers, and to produce a final output, which in our case is this, the prediction of the two parameter values. So now our training setup. For the dataset, we use a set of nearly 60,000 simulations, and we use 80% of them to train the network, and 20% of them we just leave aside to use as a validation set, so to assess how the network is able to generalize on unseen simulations. As input, we use a 3-channel input with a density map and 2 proper motion maps that are passed simultaneously for each simulation into the network. And yeah, you can see also some hyperparameters we set up after some trials we did with the network. And then, okay, how it works training a network. So we pass the input, and the input is labeled by the set of values of the parameters we used for the simulation. And the network processes this input and is able to give an output. And this output is the prediction of the two values of the parameter. Then we have to compare the output of the network with the input target labels. And to do that, we need to define a loss function, which measures the distance between the network prediction and the input labels. And for this kind of problem, we choose a root mean square error, which is, in this case, is actually useful to measure this distance. And so the aim of the training is to minimize this loss function, so to make the output of the network the more similar as possible as the labels that are attached to the input maps. And to do that, there is a method which is the gradient descent. So basically at the beginning, the network is initialized randomly, so the parameters of the network are random. And so also the output of the network will be far away from what we want, from the input labels. But as the training proceeds, the parameters of the network are updated in a proportional way to the gradients of the loss function, to the opposite of the gradients, actually, so that the loss function gradually goes down, and at the end it reaches a minimum in the loss landscape. And at this stage, so the network has been trained, and its output is the most similar we want to the input value of the parameters. So here I show the training results. In particular, these are the results of the trained network over the validation set. And for the prediction of the sigma k parameter, we can see that the root mean square error precision is around 9 kilometers per second over the whole parameter range, more or less. And this also translates into a mean relative error of around 4%. For the prediction of HC that you can see in the second row, the root mean square error is around 40 parsec, and the mean relative error is around 6%. So our network is able to predict with a good level of precision these two parameters on the simulation we have performed. But also another aspect is that we find a degeneracy between these two parameters. So if you, for example, look at this plot that show the residuals of the prediction of HC with respect to the target value, so to the ground truth, and the residuals of sigma k, you can see that there is a anti-correlation. So this means that, for example, if you look at the top left side of this plot, you can see that when the network under-predicts the sigma k parameter, usually it over-predicts the HC parameter. And on the other way around, if the network over-predicts the sigma k parameter, it under-predicts the HC parameter. And this could be explained by the fact that these two parameters in some way contributes in the same way to the final distribution of neutron stars after the evolution. Indeed, if we start from a population with an high kick velocity at the beginning, the population will inflate, basically. This will spread out in galactic 8. And at the same time, if we start from a population with a big scale 8 at the beginning, at the end, the scale 8 will be more or less preserved. And so also in this case, a spread out distribution in galactic 8 will be obtained. So during training, the network is trying to mediate between these two effects. And actually, also for it is difficult to distinguish the effect of one parameter, so of the kick velocity or the scale 8 parameter. This could be due to three main reasons. First of all, maybe our network is not good enough, so we have to choose another architecture that maybe can acquire more precise results and to distinguish between these effects. Or it can be a problem of the input representation we use, so that the input maps we use actually do not allow to disentangle the information between the effects of these parameters. Or it can be also a physical limitation. That means that actually the output of the simulation actually does not allow to distinguish between these two effects. So, by the way, our results, of course, have been obtained under some important caveats. First of all, we assume some model distribution for the kick velocity, which is a Maxwellian one. And of course, as we have seen, there are many other models that could explain the kick velocity distribution. So we can't directly apply our model, for example, to the observations. We have to be more careful to do that. And also our results, our good results does not reflect what could be the results on a true observed sample, at least right now. Also, the second aspect is that we consider all the neutron stars in the galaxy. So we consider as potentially detectable and potentially observable all the neutron stars in the galaxy. And of course, this is not the case. If we consider, for example, the observed sample of neutron stars with a measurement of the proper motion, and we plot, for example, the distribution of the distances from us, which is shown here in by the gray histogram, you can see that the distribution has a peak at around a few kiloparsec from us, and then it decreases exponentially. And this is, of course, due to all the observational biases and selection effect we have in the observed sample. And so an interesting thing that we can try is to see how this selection effect and also how the number of neutron stars we have in our sample influence the prediction and the results of the performance of our neural network. So to do that, we try to model the effect of the selection functions that are inherent in the observed sample using a weight function, which basically gives a probability to each simulated neutron stars we have of being detected. And the probability should be higher for neutron stars that are nearer to us and lower for neutron stars that are far away from us. And we fine-tune this selection function, this weight function, in order to match the distribution of observed neutron stars with proper motion measurement. And we find that the best functional form is one that behaves as the inverse of the distance and with an exponential cutoff. As you can see in these plots, with this selection function, the distribution in distance is pretty good matched by the simulated population with the adding of this selection function. And this distance bias is also automatically reflected in the proper motion distribution, where, as you can see, the gray histogram, which is the observed data, are match more or less the simulated plus the bias distribution in blue. So what we did then is to retrain our network, our convolutional neural network, on the simulations we used before, but this time for each simulation we selected an increasing number of neutron stars with such weight function we have defined. So we increased the number of neutron stars between 200 and 2000. So 200 is nearly the number we have right now in the observed sample. And we see here the results on the corresponding validation dataset. And we see that when 2000 neutron stars with the measurement also of the proper motion will be available, our neural network could be able to infer the value of the sigma k parameter and HC parameter with a mean relative error around 35%. And this highlighted the number of neutron stars is crucial for this kind of studies, and at least for our machine learning setup, since the more stars, the more statistics you have and the more information you have, of course. And now talking a bit about the future. So in 2027, it is scheduled to become operative a new telescope, which is the SKA, which stands for Square Kilometer Array. This is a telescope that will be developed and has been is in the phase of developing both in South Africa and in Australia. And this is gonna be very very important step forward for neutron star astronomy, since it will be one of the most powerful radio telescope that we have right now, with 10 times the sensitivity of the current radio telescope we have. And this will allow the discovery of nearly 10 times the neutron stars we have right now. And also it will be very large, with a baseline that up to 3,000 kilometers for interferometry, and this will allow a very high resolution in radio, and this will allow also the detection of neutron stars and the determination of a more precise distance, and also proper motion measurement. So SK will be crucial to further developments in the neutron stars physics. And this is a projection of what will be, for example, the map of the sky for 2000 neutron stars, when SKA will be able to detect 2000 neutron stars with a measure of proper motion, for example. And this great amount of data will be fundamental to answer one of the main questions of neutron stars physics. For example, all this data on the proper motion will help to better constrain the kick velocity distribution, and this is directly linked to the better understanding of the supernova explosion and the physics behind the supernova explosions. Furthermore, more accurate, this will allow a more accurate map of the neutron stars distribution in the galaxy. And this is important, for example, for developing more precise models of the free electron density in our galaxy to determine distances from radio sources. And also the timing data that SKA will provide us, so the period and period derivative estimates measurement of the neutron stars will help to fill the PP dot diagram, so providing more data to try to understand better the spin evolution of neutron stars. And this is actually the next stage of our project, since we have focused on the dynamical evolution, but we want to go ahead by modeling also the spin evolution and the magnetic evolution of the neutron stars. And so our future plans are, first of all, incorporating all the rest of the physics concerning neutron stars. So introducing the magnetic field and the period evolution of such sources, and of course the luminosity of these sources in radio, X-ray, and gamma rays. And for this part, it will be also fundamental the work that Daniele, Clara, and Stefano are doing in this moment on the development of a 3D model for the magnetothermal evolution for the neutron stars. And we will try also to include all the updated flux sensitivity limits for the neutron star surveys, in order to model the observations in different wavelengths, from radio to X-rays to gamma rays. And at the end of everything, when we have a overall simulation set up to simulate a population of neutron stars with all the physical features, we need to compare with the observations. And to do that, we aim to use machine learning again. And to do that, we also have to find a clever way to enhance this multi-parameter training to discover the birth properties of a population of neutron stars by looking at an evolved population of neutron stars. So our final aim will be to, for example, constrain the initial distribution of the magnetic field of the neutron stars, of the initial periods, and the initial luminosity, for example. And yeah, this is our main plan for the future. So here I show you what we are working right now. This is a little animation that show you a PP dot diagram where the stars basically evolve in time. So they start from an initial period and an initial magnetic field. And as time evolves, the magnetic field decay due to the ohmic dissipations and the Hall dissipation effect. And after the magnetic field has decayed, also the period derivative has become pretty low. And so they basically stop evolving in period and set themselves to a final spin period. And yeah, the color code indicated the initial magnetic field of these neutron stars. And this is an evolution with a total time of 10 to the 7 year. And we simulate here only 100 neutron stars just to not make the plot so crowded. And yeah, I end up with the summary of everything. So we reconstruct basically the birth dynamical properties of an evolved population of isolated neutron stars using machine learning. And to do that, we rely on simulations by varying the initial conditions, particularly on the kick velocity and on the scaled birth distribution. And we find out that a convolutional neural network is able to predict with a good level of accuracy these two parameters from by looking at the distribution of evolved population of neutron stars. Of course, this is done under some caveats, and we tried to see how these assumptions we did influence our results. And of course, the final thing is that the new observation and new data will be fundamental to try to go forward to this exploration and to find out more about the birth properties of the neutron stars in our galaxy. And yeah, this is everything. And so thank you very much for your attention, and for any questions, I'm here.
Okay, thanks a lot, Michele, for the nice overview of what you've done so far with the group. So any question, comment? I can start with one. So it's a question to you, Michele, but actually to anybody that could answer. Because when people speak about supernova birth rate, also the last article that you showed, I think it's basically it's a summary of the core collapse supernova rate only, no?
Yeah.
So the question is, the other channel of neutron star formation, which is the accretion induced, do you have any idea of the rate, if it's comparable, much less than the core collapse?
Well, this is a good question. In that case, we have to consider a more complicated scenario, since we have to consider the binary systems where the neutron stars can have and the progenitor stars of possible neutron stars can have a different evolution history, since the accretion from a companion can modify the structure of the progenitor stars of the neutron stars. So in our study, we do not consider the binary systems due to the fact that they are more complicated to model, indeed. And yeah, so I think also the birth rate has to be to be different a little. I don't know if it in excess or in defect.
Can I add a comment on this question? So there are, I'm sure that Jordi probably knows that better than I do, but there is very initial work by Freyer in 99, more or less, where they do simulation and try to compare the rate. And I think, as far as I remember, they put limits that if neutron star formed by accretion-induced collapse should be 0.1% of the current galactic population of neutron star. So it's indeed a possible viable way of producing them, but the rates are way lower.
Okay.
I don't know if there are some more modern simulations about this, but this is the one I remember.
Okay. I see there are some raised hands by Elena and Guillem. Please, Elena.
Hello, Michele. Thanks a lot for this very nice talk. Maybe I have missed that. If that's the case, my apologies. But I saw when you had like a very small training sample that the model saw a clear overfitting. But I don't know if you have shown the same plot for the new results where you get the better accuracies.
So you mean in these plots?
Yeah, so I mean, you saw a plot with the loss versus the epochs for the training and the validation sample in the first case where you had this one here.
Yeah.
And there's it seems to be overfitting, right? Because the validation loss is larger than the training loss. So I was wondering if the better results that you obtain now is because you have been able to remove the overfitting and you observe it in plots like this, or you still have a little bit of overfitting, so you still have room for improvement?
Okay, well, I think that we have still some overfitting, but we try to, let's say, keep it under control by introducing a cut in the training. Basically, if the validation metric do not improve for, in this case, 128 number of epochs during training, we simply interrupt the training, and we save the status of the network only when the validation metric improves. So in some way, we tried to avoid to reach overfitting, but yeah, indeed, some of it is still there.
Yeah, so definitely that's a very good way to avoid, classifying having a classification with a model that overfits. Yeah. But if you still see some overfit, it means that there's room for the model to improve more. So adding more examples to the training could help you on the performance.
Yeah, that's completely possible. Yeah, we have, of course, this is our first trials with this, and we have also to find a clever way to generalize this to also predict more than 2 parameters, and so maybe also our setup will be completely different in the future. So so yeah, but that's a good point. So thank you for.
Thanks to you, Michele. Very nice talk.
Okay, thank you, Elena. Guillem?
Yep, thanks for the talk. Just very quick technical question. So in terms of, let's say, hardware and power that you needed to run and test your neural networks, so what's the scale of it? Did you use multiple computers, several GPUs? It's just to scale what we have seen in terms of what would be needed, for example, to make a similar effort on another field. So did you have to invest a lot of money? Well, Nanda probably can respond to that, but a bit of the scale of the hardware you needed and the computing time hours of GPU that you use for this.
Okay, so for this kind of study, we use actually we rely on the peak, and we use basically a setup with a single GPU with if I remember well 32 gigabytes, and at least this for the final setup of the peak, because in the first trials we were doing there was a smaller GPU with like 12 gigabytes, but I mean that was more or less enough for our initial trials, but yeah, if you want to train over, let's say, more than 10,000 samples, of course, the GPU, the large GPU is better, and in terms of amount of time, it will take more or less hours. So no more than 1 day, I would say, at least for our experiment.
Yeah. Oh, yeah. Okay. No. But I was wondering if it was order of weeks to train.
No.
Or of the order of hours. Then you can 1 day per day. You can. Yeah. It's different development.
Yeah.
If you have
exactly.
to work. Okay. Thank you very much.
Thanks to you.
Okay, good. Any other question? If not, we can thank Michele again for the nice talk, and see you next week.
Thank you very much.
Yep. Thank you.
Bye. Thanks, Michele.
Thank you.
Thank you, Michele.
Bye.
Thank you.
Thank you very much.
Again. Bye.
Yeah.